Okay, after that short breather, welcome back everyone. It's my pleasure to introduce Alex Yong for the next talk, and he's going to teach us the A.B.C.Ds of Schubert calculus. Over to you, Alex.
Thanks very much for the invitation. I'm really honored to speak here. I'm going to talk about some joint work with Colleen Robichaud and Harshit Yadav from the University of Illinois. I'll start by talking about theory of Schubert polynomials, which, at least in my opinion, is of quite long prominence in algebraic combinatorics. And the promise and premise of Schubert polynomials, I think, comes from, to a large extent, the fact that they provide an elementary way to formulate perhaps the central problem in modern Schubert calculus. And moreover, they actually provide a potential means to solve said problem. They are invented in 1982 by Lascu and Schutzenberger. There's a single Schubert polynomial for every element of the infinite symmetric group. And as a story, they're extremely compelling. They're very much like the textbook theory of Schur polynomials. They form a basis of all polynomials, just like the Schur polynomials are a basis of symmetric functions. They have non-negative integer coefficients. And there are even formulas that exhibit this non-negativity. In fact, quite a few formulas that I've suppressed in the ellipses. But I think that the most prominent and well-known formula is due to Sarah Billey together with Jokish and Stanley almost 30 years ago. And it's even better than that. We even have geometric explanations for the non-negativity. This is explained in terms of Grosvenor geometry by Knudsen and Miller. The original reason for introducing the Schubert polynomials can be traced back to Borel's isomorphism from the 1950s. Borel's isomorphism states that the cohomology of the flag variety is isomorphic to the coinvariant algebra of type A. That is to say, polynomials in x1 through xn, quotiented by the ideal generated by elementary symmetric polynomials of positive degree. Borel's isomorphism tells you that there's this isomorphism globally like this, but it doesn't tell you how to send the Schubert classes. So these are the objects that were thankfully introduced in John's talk. The cohomology classes of that map to cosets over here in the coinvariant algebra. And the statement is that there are many possible choices of coset representatives for the Schubert class. However, Lascu and Schutzenberger are essentially saying that we are giving you a very natural, combinatorially natural choice with a lot of wonderful properties. And so this brings us to what I'll call the lifting dream of algebraic combinatorics, or combinatorial Schubert calculus. The lifting dream says that, well, the Schur functions have all these wonderful properties, and the Schubert polynomials seem to match them in almost every extent. Nice combinatorics. We understand their Newton polytopes very well now. We understand formulas, many formulas for their expansion. So why can't we understand the ring structure? The Schur polynomials multiply with structure coefficients being the Littlewood-Richardson coefficients. And this governs Grosmani and Schubert calculus. So this is part of the textbooks. We've solved this. And there are many rules for this. However, maybe one way to formulate the statement is that if you think of the Schur polynomials as a generating series for semi-standard tableau, then multiplying two semi-standard tableau, roughly speaking, you should think of as being some non-commutatively as some sort of a Schoenstatt operation, which gives you a bijection, one output being a tableau and another output being something that is counted by the LR coefficient. So it's a beautiful story. And we also have a very similar thing here. We have, let's say, the Billey-Jokish-Stanley formula that's graphically represented in terms of RC graphs or pipe dreams. So maybe we should try to do some sort of Schoenstatt-like operation that gives us a combinatorial rule for the structure coefficients of the Schubert polynomials. Right? These are structure coefficients because, remember, these are a basis of polynomials. So a priori, there are some structure coefficients, but what geometry tells you is that these coefficients are non-negative. And therefore, it is the main problem of Schubert calculus, in my opinion, to give a combinatorial rule for these non-negative integers. Okay? And people have tried this sort of thing. In fact, probably multiple people, people who publish papers on topic, and probably many people who haven't published papers on the topic. But as you can see, the problem remains to this date unsolved. There are many, many other contributions to the theory of Schubert polynomials. We could talk about contributions to other cohomology theories, but for this talk, I want to emphasize contributions to other Lie types. And even here, the number of authors is extremely large with multiplicity and with combinations. So I'll name a few: David Anderson, Fomin Kirillov, Bill Fulton, Alain Lescaut, and in orange will be a list of names which are especially important in the conversation I'm going to have later in the talk. Starting with work of Pragacz in either the late 80s or early 90s, depending on the publication date, all the way to a series of papers of Tamvakis over the last decade. Okay, so I've told you about the main problem of Schubert calculus. We cannot solve the problem, so therefore let me make a more complicated problem that I also cannot solve. You have group actions on the flag variety and on the Schubert varieties. In particular, the torus of invertible diagonal matrices fixes a Schubert variety. And the upshot of this is that we can talk about something called equivariant cohomology of the flag variety. This is an enriched cohomology ring. Okay? And the stability of the Schubert varieties under the torus action means that we can also talk about the equivariant Schubert class. So I'll denote this by Xi of W. And the picture is very, very analogous to the Schubert polynomial situation. I can talk about multiplying two equivariant Schubert classes and expanding in the basis of equivariant Schubert classes. But there's one complication to the problem. We have structure coefficients, but here the structure coefficients are actually polynomials themselves. It's a little confusing. You have Schubert polynomials, and now you have the structure coefficients being polynomials. Okay, why is this a generalization of the problem we cannot solve? Because in the special case that the inversion lengths, or in general, the Coxeter lengths of U, V, and W, the inputs to this Schubert structure coefficient add up in this way, then we get back the classical coefficients, the classical non-negative integer coefficients. It's even better than that. Something that was conjectured by Sarah, Billy, and by Dale Peterson, and given a proof about 20 years ago by Graham, is that although we know that these Schubert structure coefficients are polynomials in these simple roots, you think of these alpha 1 to alpha r as being simple roots of your root system, they actually themselves have non-negative integer coefficients. Okay? Hence, we can talk about a complete generalization of the problem we cannot solve. You can ask for a combinatorial rule that describes this polynomial and does so with a counting formula, so that the coefficient of a particular monomial counts the number of such and such that do so and so. Okay, that brings us to the thought experiment I'd like to address today. Does this extra complication help? Or is this just reckless generalization? You know, we can't solve a problem, so let's just generalize and solve a special case. Is that what we're doing? Well, this goes back to something my symplectic geometry friends would call the Atiyah-Bott principle. It's a famous paper also from 1982. And their paper has nothing to do with Schubert calculus. It's just about, but it is seminal in the sense that it shows you how equivariant cohomology, equivariant complication, can solve problems in geometry that are formulated only about the ordinary cohomology. So you have an extra lever coming from equivariant cohomology. And we could be more technical about what that means in various ways, but that's the summary I'd like to give. And indeed, a few years later, Qasim Kumar study the equivariant cohomology of a generalized flag variety. And here is, in some sense, the Atiyah-Bott principle in action already. When you do things equivariantly, we have a replacement for Borel's isomorphism. We can use something like a Borel isomorphism. We could do it by something like a, let's just say, a equivariant coinvariant algebra. But when you do things equivariantly, you have a different trick you can use. The trick is that you can actually embed the equivariant cohomology ring inside a direct sum of polynomial rings. Functionally, this means the following. Instead of thinking of a Schubert class as being a single polynomial, we're going to think of them as n factorial many polynomials, or in general, the size of the Wahl group many polynomials. Okay, so here's another polynomial being introduced. So to summarize, we have the Schubert polynomials that we study very well in the algebraic combinatorics theory. We have the Schubert structured coefficients, which are themselves polynomials, and then the Schubert classes have many polynomials in them. These are what I'll call restriction polynomials. The great thing about this is that we can do cup product multiplication without relations. Multiplication is just point-wise multiplication of these restriction polynomials. So if you want to think graphically, imagine that your Schubert class is a picture of Bruchau order, and you're assigning a polynomial to every vertex of Bruchau order. And when you want to multiply two Schubert classes, you just multiply vertex by vertex. This is great because in the 90s, work of Sarah Billey and earlier work of Anderson, Janssen, Soergel give us combinatorial positive formulas for these restriction polynomials. So we have the general ring, and we also have how the individual vertices look like. Instead of stating the whole formula in gross detail, let me just give an example. And if I say it right, I think that you'll understand how the combinatorics works and everything about it. So my example will be flags of C3. I'm trying to calculate one of these polynomials where V is W0, 321, and W is 213. Step one of the Billey formula is to choose a reduced word of V. So I'll choose S1, S2, S1. Then what you do is you find all the subwords, this reduced word, that equal W. So one of them is this blue one, choose that S1 and ignore the rest. And the other one is this red example where you choose S1 and you ignore the rest. Okay, so this one's actually, let me do this one first. What you do, it's a little confusing, but let me say it. You take the fact that this is S1 and replace it by its corresponding simple root, because S1, it corresponds to E1 minus E2. And then you just let the Wahl group act using every one of the other generators that come before it in R. So acting on this by S1, S2 gives you E2 minus E3. In the red case, it's more boring because you replace this by E1 and E2, but there's no generators to come before it. So there's nothing to do, and you just recover E1 minus E2. And in this case, Billey's formula just simply says, add red and blue, at giving you your answer for the restriction polynomial. In general, this case is a little bit specific because the reduced word for W is just one generator. If there are multiple generators, then what happens is you carry out this process multiple times and multiply all the answers and add them up. But this is essentially the whole formula. And this is a formula not only for type A, but for any type any valid type, Lie type. Okay, so we talked about the lifting dream of algebraic combinatorics, that we're going to take Schur polynomials, lift it to Schubert polynomials, and solve Schubert calculus. Let me talk about an alternative to the lifting dream, which also explains the title of the talk. I want to call it Atiyah-Bott Combinatorial Dream, A, B, C, and D. The statement is that something true about the restriction polynomials combinatorially is also true of the Schubert structure coefficients. So it's an analogy of an analogy, right? The analogy is that anything true of Schur functions should be true about Schubert polynomials, and that's the lifting dream. And here I'm saying anything true of these simpler things, these restriction polynomials, is true of of the big kahuna.
Alex,
Yes.
before you go on, just a quick question from Darij.
Mhm.
If you go back one, yeah. So is this a direct sum of rings or well, a direct product of rings or a direct sum of modules at the third line?
You're asking about this?
Yes.
Yeah, right. So it's a module over HT of a point, which, I mean, ignoring duals, I'll just think of it as being over this.
Okay, so it's not a direct product of rings or just as modules.
What I
Yeah,
mean is,
that's right. Exactly. Correct.
Okay.
Thanks.
But does that answer your question? Like you're doing pointwise multiplication of lists of polynomials, right? Does that answer your question?
But how can you get the C's if you cannot if the multiplication is not coordinate wise?
It is coordinate wise.
Oh, so it is a direct product of rings.
Right.
Thank you.
Oh yeah, sorry for confusion on my part. Okay. So A.B.C.D is that something true about the restriction polynomials is true about the big kahuna, the thing that we like to compute. And first statement is that already 30 years ago, the converse of this was known to be true, meaning that every restriction polynomial is a special case of the problem that we cannot solve. Okay, so obviously anything we know about the combinatorics of this will give you back combinatorics of the restriction polynomials. Second example that's sort of prominent is that it's already fun from, let's say, even a textbook exercise in Coxeter theory to ask somebody, why is it that this polynomial has non-negative coefficients in the simple roots? Okay, and what Graham did, what we would like is to take that textbook solution and generalize it to this situation. If we did that, we would have a combinatorial proof of non-negativity over here. What Graham does is gives a geometric explanation. Okay, so let's be honest. The dream obviously isn't always true, right? However, the point I want to make is that you can be concrete and definitive in experimentation. You can get new experiments through thinking about A.B.C.D and check whether they're true, rather than just fantasize about the possibility of something. Indeed, we do get some new conjectures, and one of which is of some relevance in my own interests, connected to Horn conjectures. But of course, the ultimate question is, can one quote unquote see the solution to the main problem by staring at the combinatorics of the restriction polynomials in some sense? And this is not as crazy as it sounds, because very recent work of Knudsen and Golden go a long way towards this. They in fact do generalize Billey's formula to the entire problem. However, their formula is not positive. All right. So whether or not you think that A.B.C.D does any better than the lifting dream, let me just say that it's an organizing principle to understand earlier work of many people, as well as the results of this talk. Okay, let me tell you about a certain correspondence of Schubert calculus kind between two Lie types. And this generalizes the theorem of Pragacz with a new proof. So just like in type A, we have the ordinary flag variety of subspaces of complete flags of subspaces. In a type Bn and Cn, you have something very analogous that are called isotropic spaces. And for sake of time, let me not define them in complete generality, or with much generality. Let me just state them as existing. And let me tell you what we noticed by example first, and then I'll formulate the theorem. Okay, so I'm interested in the Schubert structure coefficients of X and the Schubert structure coefficients of Y. We also don't know how to solve those problems. However, there's a relationship. As you know, the Weil group of type B and C is the hyperoctahedral group. So here are my sign permutations, my input U, V, and W. And let me compute the coefficient associated to u, v, and w for type B. It's given by this polynomial where the betas are the simple roots of type B. Let me also compute the same thing for y, the type C coefficient. You'll see you get a very similar polynomial, right? And you'll notice that some of the numbers are the same. For example, the blue ones, 10 and 10. And sometimes the x beats the y, and sometimes the y beats the x. But the Newton polytope is in fact the same, right? The same monomials. What my former student noticed, Monical noticed, is that there is a power of 2 difference. But the power of 2 can sometimes be with negative exponent. Okay, so for example, 6 is 2 times 3, but 4 is 1/2 of 8. Okay? And that, to be absolutely honest, surprised me a little bit. No, actually, you know, of course I was aware that there should be some power of 2 relationship. That didn't sound so surprising, but it was news to me. And so I went to a Schubert calculus conference at Ohio State in 2018, and I told many people, I said, I announced this conjecture, and I said, does anyone have an explanation for this? I didn't get any answers. Okay, here's how you can reconcile the situation. You take gamma 1, just gamma 1, the funny root, and you replace by twice beta 1. And then you replace all the other roots by their corresponding things, gamma 2 by beta 2, gamma 3 by beta 3, and you just substitute into this polynomial, and you'll get something that is twice of x's polynomial. And you fix that by computing a statistic, this statistic associated to the signs, the number of sign changes in u, v, and w, and you multiply by 2 to that statistic, and that gives you an exact equality between the 2 coefficients. So we don't know how to give combinatorial rules for either of the coefficients, but we do know that they are related. Okay, so this slide is just a formulation of that theorem, of the theorem that I just stated in detail. Just quickly, x and y are again the isotropic flag manifolds. You have your simple roots associated to these Dynkin diagrams. The hyperoctahedral group is the common vowel group. You have the sign change statistic. Here's the transformation that I was telling you about. And then our statement of our theorem is that you have equality. And what's the proof? The proof is what I'll call an A.B.C.D proof, okay? You just check that the statement holds by applying Billey's formula. You just look at Billey's formula and you say, yes, indeed it's true for the restriction polynomials. And then you just say, by the Kosten-Kumar isomorphism, it must be true in general, precisely because what Dari said. Okay, so it's a 2-line proof in essence, once you accept the Kosten-Kumar precept. I want to talk about some comparisons to the literature. First, a special case of this problem, non-equivariantly, so in the original context, and not for flag varieties, but just for Grassmannians, was due to Pragacz. He says that in that situation, you have 2 numbers, not polynomials, numbers, and one is controlled by a power of 2 by the other, period. Now, again, not equivariantly, but for the actual full flag varieties x and y, this was first noticed in print by Bergeron and Satile using the Schubert polynomials for classical groups defined and constructed by Billey and Haiman in 1994. As I said, Monical first noticed this relationship, at least noticed this relationship between the x's and the y's. And after we found our proof, we of course did our due diligence and looked at whatever papers we could on the subject. And we looked at Ikeda and Mihalcea and Naruse's paper on equivariant type B, C, and D Schubert polynomials. And yes, we could prove it also using that. And also there are papers of Tamvakis which talk about what he calls the theta and eta polynomials. And there's a lot of work on type B.C.D equivariant, ordinary Schubert polynomials and equivariant and so on. But as far as I can tell, they do not state this theorem that I'm asserting, right? A little bit more evidence that at least not every expert knows about this kind of relationship. In 2016, a wonderful paper by Lee and Ravi Kumar give Pierre rules in this context. And what they do is they give a geometric proof in type B and in type C. What we're saying is that with this correspondence, you can, of course, have their paper. If you know the BN results, you automatically can derive the CN result. Now, I don't actually want to quibble about whether or not it was known about to experts or not known to experts, or whether it could have been derived from this thing or could have been derived from that thing. My main point is that you can replace the entirety of Schubert polynomial theory with an older, more general framework. And once you observe the result is trivial. Let me tell you another fact that I'll state. So let's suppose I'm interested in not only classical types, A, B, C, and D, but exceptional types, perhaps. Is there a relationship between the Schubert structure coefficients of, let's say, type E8 and D4? Well, the answer is maybe, of course, yes, right? You imagine G prime corresponds to D, this is the D4 Dynkin diagram, it embeds into E8. Then what this statement says is that up to the obvious transformations, right? Meaning that the embedding of the Dynkin diagram leads to embedding of the Weil group, it leads to embedding of the root bases, then you can compute that E8 coefficient from knowing certain E8 coefficients from knowing the D4 coefficients. And in particular, this applies in those exceptional types where there is no suitable Schubert polynomial theory whatsoever. What's the proof? It's an A.B.C.D proof, meaning that once you observe such a statement, you check it using Billey's formula, which is again not difficult, and then you apply the Kosten-Kumar yoga. Okay, conclusions and summary. As I said from the beginning, the premise and promise of Schubert polynomial theory seems great, and I think it is a wonderful subject. I love them. I have made a good part of my career thinking about them. And they are defined from the perspective of Borel's isomorphism. A.B.C.D stems from a different isomorphism, the Kosten-Kumar isomorphism, which is something that only exists equivariantly and is genuinely different. There is significantly less literature in our field coming from thinking about that kind of dream, as opposed to the lifting dream. What I assert is that thinking A.B.C.D as a field, algebraic combinatorics can give simple new proofs of results, find concrete new possibilities, while avoiding a vast amount of Schubert polynomial theory that has developed over the last 30 to 40 years, but instead appealing to an old, more general, and in fact, more uniform viewpoint. Thank you.
All right, let's thank Alex for this excellent talk. And over to Peter for the questions.
Yes, so I see that, well, I saw that Greta has a question. No, it was a clapping. Anyone has a question? Sam?
Hi there, nice to talk, Alex. So you discussed kind of duality of Dynkin diagrams and inclusion of Dynkin diagrams and how they affect these equivariant coefficients that you were looking at. Maybe another obvious thing, which I don't know if you have looked at or not, is automorphisms of Dynkin diagrams and folding. Is there a simple effect that has on these equivariant polynomials?
So there's this is something we examine in our paper. So for example, BN and DN coefficients, it does seem to be some relationship, and we formulate the extent of this of what we could understand, but it wasn't as, we couldn't quite figure out the clean statement, right? But certainly you think there would be, and there are certain cases where there are, but we didn't quite write them all up. But yes, in those cases there are, you would apply the same, presumably the same A.B.C.D philosophy. You just check it on the restriction polynomial, then it will be true in general.
Thank you. Zachary?
Hi, Alex. Really nice talk. I had a question, which is how much of this machinery extends to other cohomology theories, and specifically I'm interested in K theory.
Yeah, so I have to admit that although again I've thought about K theory quite a bit, we have not thought about the exact details for, let's say, equivariant K theory. That's right. Mm-hmm. There are some things there's a little bit of technical complications there that confuse me. It's my fault. It's really my lack of my great confusions about various things. But you would think that it should go through, but I mean, machinery is an overstatement. It's basically, let's call it a philosophy, building on earlier work of others.
Okay.
So thank you. I don't see any more questions.
I have my hand up. I have my hand up.
Yeah, but no virtual hand. Yeah, but go ahead.
Well, my little clappy symbol, I don't know. I don't have all the options that you have. So, Alex, great talk once again. So my question was, you brought to light something that I hadn't thought about at all before, sort of, how do you interpret the coefficients that are coming up in the equivariant cohomology formulas? Is there some way to interpret those positive integers in a geometric fashion that's on par with the classical interpretation of the Littlewood-Richardson coefficients and their generalizations?
For that, the sort of prevailing paper would be Graham's paper, right, where he gives a geometric explanation of the formula by a degeneration argument. However, my understanding is that it isn't as clean, right? As you know, for the classical situation, it's just the triple intersection of Schubert varieties, right, the number of points in the intersection. I don't think there's a formulation like that equivariantly.
Something to work on. Back to you, Petter.
Back to Vasu.
I see that Liz has a question, so maybe I'll just say it out loud. Alex, Liz is curious to know what you're working on next using this philosophy.
Well, I mean, okay, so we all have our favorite, famous problems to try to work on. This one happens to be mine. So maybe best way to say it is that once every year, you take a couple of days and you try to solve the famous problem, all right? So, so obviously I would like to solve the famous problem, but if I had that, I would have talked about it, right?
All right, if there are no further questions, let's thank Alex again for the excellent talk.